when we have a reaction, a lot of times you're going to have some type of temperature change or heat change, energy change in the reaction, okay? So if you guys take a look at this example, we have a chemical reaction and we have a delta H next to it. And so the delta H tells you whether the reaction released energy or it absorbed energy, okay? So in this reaction right here, this is what we did last time at the end of class when I blew up that balloon. Okay, we got some hydrogen gas, reacts with oxygen gas, and obviously you guys saw a fireball, and so that means the reaction released energy, okay? And this delta H is basically the difference between the enthalpy of the products and the enthalpy of the reactants, okay? Okay, so if delta H is negative, the reaction is exothermic, so energy is a product, energy is released, okay? Make sense? All righty. Okay, so we're going to be analyzing some chemical equations in a sec, but before we do that, I need you guys to know a couple things about the enthalpy of reactions, okay? So the first thing is that enthalpy is an extensive property. Basically, what it means is that it changes in proportion to the reaction. So here, if we look at the first reaction, it's 890 kilojoules released, right? But if you double everything inside the reaction, if you multiply everything by 2, the enthalpy will also be multiplied by 2, okay? That's basically what it means. It means it has a linear relationship with the chemical reaction, okay? So if you double it, enthalpy is doubled. If you half everything, then enthalpy will be divided in half. That's pretty much what it means. All right, the second thing about enthalpy is that the reverse reaction is equal in magnitude, so it's the same number, but it's opposite in sign. So here we have the same reaction again. So when you react methane and oxygen in this reaction, it's going to release 890 kilojoules. But if you flip everything around, so if you want to take carbon dioxide and water, the products, and turn it back into methane and oxygen, you're going to have to put in 890 kilojoules, okay? So the difference here is that in this reaction, you're going to release energy, so energy is a product. But if you want to reverse the reaction, you need to put in energy into these molecules to make it go backwards, okay? That's what it means by being reversible, okay? Yeah. And so if you guys notice, it's negative 890, positive 890. And that tells you which side of the equation it's going to be. Okay, so theoretically, if we blow up a bomb, right? Theoretically, for the record, theoretically, I'm Korean, but doesn't mean I'm gonna blow stuff up. Theoretically, we blow up a bomb and we have all the material that was released, right? If you put energy back into those materials, theoretically, you could make it back into the bomb. You could turn it back into the explosive material. Yeah, you would, but you would have to put in the same amount of energy back into those products that was released. Yes, I did indeed. Don't worry about it. Don't worry about it. All right. I don't trust y'all. Y'all snitches. What's up? My dad's family's hometown is in North Korea, so I'm a halfie. I'm DMZ Korean. It is possible. They can leave. Yeah, that's why all those people ran away during the Korean War. They're not allowed to. But people get out very rarely, though.
Well, let's stop questions about the bomb.
All right, so the third thing about enthalpy is that the change in enthalpy depends on the state of matter, okay? So when you have a reaction and you're trying to analyze enthalpy, you need to write it whether it's a solid, liquid, gas, aqueous, whatever. Because when you have a compound, so let's say you have liquid water, right? And you turn into liquid, which you're not doing anything, right? The enthalpy change is 0. There's no change in enthalpy, okay? However, when you turn liquid water into gaseous water, water vapor, it's going to require some energy. So the enthalpy changes when you're going between states of matter, which makes sense, right? If you're trying to turn water into water vapor, you got to put some energy into it. You got to boil it. You got to put heat into it. Okay, so that's the third thing that matters. It's that it depends on the state of the reactants. Oh, there should be a fourth thing. I never catch this. Oh, and the fourth thing is the enthalpy change, or the internal energy of gases is usually higher than liquids, which is usually higher than solids. Okay, which makes sense, right? Because the molecules are moving around the most in a gas, is moving around a little less in liquids, and then it moves not much in solids. So gases have more internal energy generally than liquids and solids. Yeah.
So that's like when you have a solid.
Yeah, that's why you need to put energy into a solid to make it a liquid, and then more. It's usually when you're comparing different compounds, but within the same substance, it's gonna follow that trend. Yeah, I'm sure there's some weird exceptions that somebody can find, but we're talking in general. Okay, so let's go on to 6.15. So we got a chemical reaction here. I know this might be kind of hard to see for you guys, so if you guys have it pulled up on Canvas, that might be helpful. But what we're going to do is we're going to find the enthalpy change in the reaction above per mole of CO2, okay? Per mole of CO2. So I'm going to do this problem with you guys, and then I'll have you guys try the next one on your own, okay? So you want to find the enthalpy change, so you want to find the delta H when you have, or per mole of CO2. So if it's per mole, what's the number that we start with? Yeah, 1, yeah. Yeah, because if you're going 65 miles per hour, 60 miles in 1 hour, right? If you have 12 eggs per dozen, that means you have 12 eggs in 1 dozen.
10,000 medical students in Spain.
I don't get that. All right. Okay, so you get 1 mole of CO2, okay? I did not get that one. Okay. Okay, so we got 1 mole of CO2, and we want to do a quick conversion factor. Now I want to get rid of moles of CO2, so I'll put that on the bottom. And you're looking for the change in enthalpy. Enthalpy is measured in terms of kilojoules, so kilojoules on top. Okay, so here you can just look at this as a part of the reaction. Okay, so inside the chemical equation, we're working with 4 moles of CO2, and 4 moles of CO2 is going to release 3,120 kilojoules. So you can just set it up just like that. Okay, so going forward, if you have an enthalpy change, you can just treat it as part of the reaction, whether it's a reactant or a product, depending on the sign, okay? Make sense? Any questions? Okay, so I'll just give you guys an answer for that one. It's going to be 700 or negative 780 kilojoules. Okay. So the enthalpy change is going to be negative 780 kilojoules. Another way that you can describe this is you can say that 780 kilojoules is released per mole of CO2. Doesn't really matter how you write it, as long as you understand what that negative sign means. Yeah.
Do we need to notate that we're talking about CO2 in our answer?
No, that's fine because it's asking for it. Yeah.
They ask you for like the O2 instead of CO2, they still
You can still ask for that enthalpy change, yeah.
so then
Yeah. Just the only difference is if it was positive enthalpy, then it would be part of the reactants. So it'd be like this, so it'd be a positive sign, but if it's negative, it's part of the products.
yeah, how do you do it?
Same thing, just positive number, and then you get a positive answer. And instead of it being released, it would be absorbed.
Oh.
Yeah. So that's the only difference. Any other questions? Okay, let's move to part B. Okay, do the reactants or products have a higher enthalpy under these conditions? Okay, so if you guys remember, the change in enthalpy, the formula is the enthalpy of the products minus the enthalpy of the reactants. Okay. So if the enthalpy is negative, which one is going to be higher, the enthalpy of the products or the enthalpy of the reactants? Yeah, the reactants is going to be bigger, right? Because you're taking away more than you have for the product. So that means the reactants is higher. Okay, there are two ways you guys can explain this. You can say because of this equation, you can use this equation as your explanation. You can also see that remember that fourth point, the one that I put in just now. Internal energy of gases is usually higher. You got two gases, or you got 9 moles of a gas, 4 moles of a gas, and liquid. So there's more gases on this side, and so that's another reason why it would have higher internal energy.
So it's whatever like numbers are regardless of
What? Wait, sorry, I didn't understand your question. Could you?
so like it came out as a negative, so
Uh-huh.
that's
So since the enthalpy is negative and this is our equation, let's do x and y. In order for the difference to be negative, this number has to be bigger, right? The magnitude of this number has to be bigger than the x, okay? Yeah. Mhm. Yeah. Oh yeah, so this is a equation that was up there earlier. Hold on. So we don't know what the internal energy is. We just know the difference. We see that the difference is a negative number, right? Okay. Yeah, this is what's going to happen. We don't know how much internal energy there is here. We just know that this number comes from the difference between these two. You have to subtract products and reactants. It has to be bigger. We don't know the actual number. Yeah, we're just looking at this conceptually. So for example, let's say, we don't know if this is true or not. Let's say the products is 10, okay? The internal energy. The only way for the change in enthalpy to be negative is for this number to be bigger than 10, right? It has to be bigger than 10. If it's smaller than 10, you'll get a positive number, right? And so that's why the reactants have to be bigger if the change in enthalpy is negative. Yeah, it's because of this equation. That makes sense? Kind of. We're going to do another problem like it, so hopefully that kind of helps out. But yeah, just focus on this equation. It's just replace this with like signs. Like if this is negative, that means this value has to be bigger. Okay, yeah. Because of the sign right here, it's negative. So for like, again, for example, if this let's say the internal energy is 10, right? In order to make a negative number, you have to pick a number that's bigger, like 11, right? But if I pick something that's smaller than the energy of the products, like let's say I pick 9, can I get a negative number if I'm doing something smaller than 10? You can't, right? Okay, for sure. I just need to put numbers in. Exactly. Cool, nice. I'm glad. No, you're good. This is what we're here for, to answer the questions. Okay, guys. So last one. I'm gonna erase all this so it's easier to see. So if you guys notice, we used gaseous C2H6 right here, right? C is asking if we used a liquid instead of gaseous C2H6. Do you think that delta H is going to be bigger, smaller, or stay the same? So instead of gaseous, we used liquid. Okay. How do you think the delta H is going to change? Is it going to go up? Is it going to go down? Or will the number stay the same? Okay, so I'll give you guys a minute to think about that. And then after that, we will move on. Take your time. Okay, so we're comparing a gas and a liquid. Okay, so I'm going to do it up here for part C. But we're gonna need that internal energy formula again. So of the products minus the reactants, okay? So easiest way to think about this is to look at what we're changing. So what has more energy, the gas or the liquid? Yeah, the gas has more energy, right? And this has less energy. Okay, and so for the original reaction, you had negative 3,120 kilojoules, okay? Now, if we turn it into a liquid, that means we have less energy on the reactant side. So the magnitude of this number, is this number going to get bigger or is it going to get smaller? Yeah, this number is going to get smaller. Okay. So if we substitute the gas for a liquid, this value is going to get smaller. Okay. So if this number gets smaller, is the magnitude, again, we're not focused on the sign, is the magnitude of the number going to get bigger or smaller? Yeah, this is also going to get smaller. So that means it's going to decrease. Okay, so it's increase in the sense that the delta H, when you change it into a liquid, it's going to be probably like, I'm gonna throw out a number, but it's gonna go in the opposite direction. It's gonna become a higher number, but the magnitude of the number is going to get smaller. Yeah.
So it's like absolute.
Absolute, yeah. That's what magnitude is. Yeah. Yes, then it's going to increase. Yeah, exactly. Yeah.
So like, how would you say that? Do you say that the enthalpy got higher, or do you say got lower?
So a way that you can describe it is you could say the internal energy in a liquid is lower than the internal energy of a gas. Therefore, if we use a liquid instead of a gas, the magnitude will decrease.
Oh, so you don't have to say like.
Yeah, you don't need to get the numbers or anything. Yeah. Okay. Cool. Good questions, guys. Any other questions? Alrighty. Guys think you can try one on your own? All right, let's try one on our own. So we're gonna go to 6.16. There's part ABC. So I will give you guys maybe like 4 minutes to try it out. You can work with the person next to you, and then after that, we will go over it. Oh, we have a lot of time still. Alrighty, guys. So since the enthalpy for 6.16 is positive, that means the reaction is endo. Yeah, endo. Okay, it's endo because this means that it absorbed heat. Okay, it absorbed energy. And also it means that heat is a reactant. Okay, it needs heat in order to start the reaction. Okay. Alrighty, let's move on to part B. We're going to calculate the amount of heat. Obviously, that means kilojoules. That's transferred when we start with 10 grams of nitrogen gas. And luckily, it's excess oxygen, so we don't need to do limiting reagents. Okay, okay, so 10 grams of nitrogen gas. And again, we're just going to do or I guess this is thermostoic now. But we're going to use the molar mass, so 28 grams of N2 per every 1 mole of N2. If we look at the reaction, every mole of nitrogen gas is going to require 67.6 kilojoules to be absorbed. And so for your final answer, you should get 24.143 kilojoules. Okay. And to specify, because it is positive, that means it was absorbed. You guys don't need to write that, but just make sure conceptually you understand. Okay. It's a positive value, and if it's positive, it means it's absorbed. Okay, you're adding to the system. Make sense? Just making sure. I'm just making general eye contact. What's your question on this one? Let me.
No, I just.
Okay, yeah, no, we'll go over it. So, enthalpy change. Okay. So if it's positive, that means that it absorbs this energy, right? So if we have, again, another one of my beautiful drawings, let's say this is the reaction, okay? This is a system. When the system absorbs energy, okay, let's say the system, think about your phone, right? Your phone's at like 95%, and it absorbs energy. right? It's gonna increase, right, in the energy, the energy inside of it, right, to go to like 100%. Okay, so it's absorbing energy. So the delta H, the change in energy, is positive because it's absorbing. That makes sense? Okay, whereas if it was negative, it means that it's going to have to release energy. It's gonna put energy out of the system. Okay, so it'd be like your phone opposite. You're using energy, you're releasing energy from the system, and then so the internal energy in your phone is gonna go down. Yeah, heat is a product. Heat is released. Like if you have your phone and your phone gets really hot, right? It's releasing heat. It's using energy. So the energy inside the phone is going down. Yeah, just like that. Does that help? Yeah.
So this is that, it's almost.
Yeah, so if we were putting this enthalpy into the equation, it would be 67.6 kilojoules on the left side. Sorry, Stan, do you have a question? Okay. Yeah, so we know it's endo when the system absorbs heat, okay? So here, let me do endo first. So endo means that it's going to get heat from the surroundings, okay? So if it's gaining heat, right? Let's say we have, I don't know, again, like the phone battery. If your phone is at 50%, right? And your phone absorbs energy, what happens to your percentage, your battery percentage? It goes up, right? So that means the system, if it started at 50 and then it goes to 100, that means there was a positive change in the energy, right? That means it's endo. Your phone is absorbing energy. And so the delta H is positive because the energy inside is going up. Make sense? Okay, so that's why positive enthalpy change means endo. Okay, but if your phone, like when you're using your phone and your phone gets really hot, right? You know, that means obviously it's releasing energy, right? And what happens to your phone battery when it gets really hot? It goes down, right? So the internal energy is going down. That'll be exo and negative energy. Yeah, kilojoules is positive, so it's a reactant. That means you need to put in energy in order for this reaction to start. Yeah. That help? Yeah, it's a little confusing because it seems like it should be opposite, but yeah. Okay, let's go to the last one. This time your starting number is kilojoules. So we start with 200 kilojoules of energy. It's saying if you release this much energy, or sorry, absorb this much energy, then how many grams of NO2 do you make? So same thing here, we just use our stoichiometry. So 67.6 kilojoules per every 2 moles of NO2. And then we can convert that into grams with the molar mass. 1 mole of NO2 is going to be 46 grams of NO2. And then that's going to give you a final value of 272.189 grams of NO2. Okay. So hopefully the stoic wasn't too bad. Alrighty, any questions? Isn't thermo fun, guys? I love thermo. When I said it was my favorite, you thought it'd be really bad, right? Yeah. I'm glad. My least favorite is electro, so. I think it's harder. It's a lot more conceptual, and it kind of synthesizes a lot of the stuff we learn now in it, so. And we only have like a week to cover it. But it's a short unit. Okay, let's move on to we'll skip 6.17 because it's kind of similar questions. Okay, and then we'll end today with Hess's law. Now, Hess's law is a lot of fun. Oh, it's just fun. It's like a game. Okay, so Hess's law basically tells us that, or let me preface that. So sometimes a chemical reaction doesn't just happen in one step. Sometimes there are multiple steps in order to get a reaction happening. So for example, let's look at the 6.18 example. We have a reaction right here, right? Okay, you take methane, oxygen, and you make carbon dioxide and water. Okay, now even though we write it as one equation, this is actually a reaction that takes multiple steps. Okay, and these are the steps that take place. First, you react the methane and the oxygen, and it produces carbon dioxide gas and water vapor. But then the water vapor is going to have a reaction and turn into liquid water. So it's a multi-step reaction in order to get this. Okay, and so what Hess's law tells us is that if there is a multi-step reaction, we can find out the enthalpy change of the total reaction by using the steps that it takes. Okay, and so you're basically combining reactions together in order to find the enthalpy change for a multi-step reaction. Okay, so sounds a lot more complicated than it is. What we're going to do is we're going to just do 6.18 and let's see if you guys can do another one on your own. Okay, so I'll show you how to do this one. So first thing that you want to do is you want to identify what you want to keep and what you want to get rid of. Okay, so we're trying to find the enthalpy change for this reaction, right? So we want all of these molecules, but anything in here in the steps that isn't at the very end, we want to get rid of it. Okay. So let's start with CH4. So CH4 gas, we want to keep CH4 gas, okay? Oxygen gas, we want to keep oxygen gas. CO2 gas, we want to keep. And liquid water, we want to keep. So these are the 4 things we want to keep. So what do we want to get rid of? Yeah, we want to get rid of the water vapor, right? The H2O gas. Okay, and so what we're going to do is we're going to try to put H2O gas, one on the left side and one on the right side, okay? Because if you have one H2O on the left and the right side, they can cancel each other out, okay? Which makes sense because if you have 2 H2Os here, these can turn into water vapor using this reaction. And so once you get rid of what you don't want, and then just double check all you want, the only things left over are the things that you wanted. So we got this, we kept everything. Cool. Now we can just add up the enthalpy changes, and that will be the enthalpy change of this multi-step reaction. Okay. So we can just add negative 802 with negative 888, and that should give you negative 890. So this is going to be your answer. Yeah, what's up? Yeah. Yeah, so the next one I'll show you, you're gonna have to change some things. So we're gonna have to use the rules that we learned earlier about if you reverse it, you have to change the sign of the enthalpy. If you multiply it by 2, you gotta multiply the enthalpy by 2. So it gets a little bit trickier, but same general premise. All right, any other questions? All right,